In a previous video, or maybe in your physics class, you learned how to add vectors graphically. For example, if we had one vector that looked like this, and another vector that, say, looked like this. A way to add them would be to redraw them, keeping their magnitudes and directions the same, but placing them so that the initial point of one vector is on the terminal point of the other vector. So I'll copy the first vector about like this, and place the second vector, arrowhead to endpoint, about like this. And then what we call the resultant vector, or the sum, is the one that looks like this, from where you first started to where you finish. You might call it, again, the shortcut. Okay, it's the same as taking a walk this way. Taking a walk this way has the same result as if you take a walk this way and for this distance. By the way, that's called by some people the triangle method. There's another method called the parallelogram method that's equivalent to it. So that's how you add vectors graphically. Today we're going to learn how to add them mathematically, but we're going to do it the easy way. What we're going to use are what are called components of vectors. You see, the idea is every vector can be broken down into components in the x direction and the y direction. That is, vectors that are in two space, meaning the xy space. So we start with a circle. And in that circle, let's suppose that we have a vector A that's at an angle theta. Now, when I talk about an angle theta, I'm talking about the angle measured from the positive x-axis like this. As is usual, the horizontal axis we will call x, and the vertical axis we will call y. Okay? So that's what we mean. In this case, theta is more than 90 degrees. Now, what you can do is think of that as the shortcut, say cutting through the backyards instead of following along the street. What do I mean by the shortcut? Well, if we had followed along the streets, starting at the origin, we might have gone to the left a certain distance that we'll call a sub x, that's called the x component, and then a certain amount up, which we'll call a sub y. That's the amount in the y direction, or the y component of the vector. And so any vector can be broken into its components. Now, if the vector happens to be along the x-axis, then it has an x component and its y component 0, similar for the y-axis. But that's basically how you do it. Now the question is, how do you compute those? Well, if you've had some trigonometry, you already know. You know that the x component is a, that is the original vector's length, times the cosine of angle theta. Note that in this case, with theta over 90 degrees, that cosine will give a negative answer. And by the way, if you don't get the right answer when we're going over an example, check to make sure your calculator is in degree mode. The y component, that's a sub y, is a times the sine of theta. Think about cosine as being related to adjacent and y component as being related to opposite, and I think sine and cosine will make pretty good sense. If you start with the components, you can reform the original vector in the following way. First, by using the Pythagorean theorem, because you see, except for vectors on the x-axis and the y-axis, you always form a right triangle, which means you can always use the Pythagorean theorem, you know, the one that was misquoted by the scarecrow at the end of The Wizard of Oz. And that would say a squared equals a sub x squared plus a sub y squared. Here I took the square root of both sides. So if we want to find the magnitude of the vector and we already know the components, we can do that. What if we want to find the angle? Well, if we know the components, we know that opposite over adjacent is tangent. So we have the tangent of theta is a sub y over a sub x. Then use the inverse tangent function on your calculator, and you can get the angle. Now, actually, what you'll get for the angle is an angle that's either in the first quadrant right here, or in the fourth quadrant down here. So you have to be a little bit careful. If you were finding something in the second quadrant or third quadrant, we would have to take whatever answer the calculator gives and add 180 degrees to it. So your calculator might give an answer for the angle as being down here. Add 180 to it and you'll get the correct angle up here. Got it? Okay, great. I knew you would. So the general idea then for using the component method is first determine the coordinate system. Where is your origin? What are your positive x and y directions? Second thing, find all x and y components of any vectors, and it doesn't just have to be 2 of them. It could be 3, 4, or more. Find all the x and y components, and then you combine all the x components with each other and all the y components with each other. And you'll see how to do that in a moment. Draw a sketch of the resultant. Notice that we haven't even drawn a sketch yet. We could have, but it's not absolutely necessary sometimes. And then finally, use those last 2 formulas we had on the previous slide to find the magnitude and direction of your resultant vector. You can do the whole thing mathematically. All right? All right, let's try an example. A velocity vector has a magnitude of 54 meters per second at an angle of 53 degrees west of north. And another has a magnitude of 71 meters per second at an angle of 22 degrees south of east. Find the sum of the 2 vectors. Okay. Well, first thing we need to do is get well organized here. So let's write all of this stuff down and name these vectors. So let's call that first vector, vector A. And the way we'll write it down is we'll say that it has a magnitude of 54 meters per second. I'm just going to write down the 54, but we'll remember to put those units on at the end. At an angle of 53 degrees west of north. Now, what exactly does that mean? 53 degrees west of north is going to be, well, it's kind of going to be that away, with a 53 degree angle right here. But the angle we want is this one. So it's going to be 90 plus 53, and so that's going to be 143 degrees. And let's call the second vector vector B. Let's see, it has a magnitude of 71 meters per second. I'll just write 71 for now. At an angle of 22 degrees south of east. South of east is down this way. And so we could measure a positive angle all the way around the circle like this, but I think it's easier to just write that as negative 22 degrees. So what do we do next? Well, now that we have our vectors listed, we have to find their components. And I think a nice, easy way to organize this is to form an x column and a y column. Okay? So for that first vector, it would be 54 times the cosine, remember x goes with cosine, of 143 degrees. And compute that, keeping an extra significant figure or two. And that turns out to be negative 43.13 meters per second. And now we do the same for all the rest of them as well. So there you have all of them. Now what's our next step? Well, the reason I have those columns is for the next step. We have to combine, by addition, the x components and the y components. Notice, by the way, that if we had a vector c, we could just put those in the same columns and do exactly the same thing. And so when I combine the x components here, let's call this v sub x. This is a velocity vector. And I combine those, I get 22.70. And over here, if I combine these two, I'll call this v sub y, and that's going to be 5.90. Okay, so we have our components. Now what do we do? Well, we have to figure out, using those components, what the final vector is. So let's begin by drawing some axes. Our x component is 22.70, and so I'll draw it starting at the origin and going in the positive x direction. And let me label that 22.7 here, just to make it a little easier to follow. And then our y component, this one, we have to add to the end. Remember, arrowhead to endpoint. And so that goes straight up because it's in the positive y direction. I'll make it shorter because, as it turns out, and you can check this on your calculators, 5.90 is smaller than 22.70. You'd be surprised. I've had a lot of students who think all vectors are the same length and all angles are 45 degrees. That's not the case. And so now we need to draw the resultant. So we go back to where we started and draw the resultant straight out to where we finish. That's it right there. And that is vector v, and whatever that is, that's the answer to our question, the sum of the two vectors. So let's figure out the sum. We know that the Pythagorean theorem says that v, the length, is the square root, draw that nice and long, of 22.7 squared plus 5.9 squared. Now, I happen to have a vector in the first quadrant here. If it were any other quadrant, one or both of these components might be negative. On your calculator, be sure that you put the number in parentheses, because that way the calculator will know that you mean to square a negative number, not to take the negative of a squared number. In other words, all these answers under the square root sign have to be positive. When we do that, we get that that's equal to 23.4. Okay, just a little bit more than 22.7. And by the way, it needs to be more than either of the components. And as for this angle right here, let's call that theta. The tangent of the angle is going to be opposite 5.9 over adjacent 22.7, and that works out to be 0.2549. Now, don't make the mistake of thinking that that's the answer. That's the tangent of the angle. If we actually take the inverse tangent of that, the calculator says that angle theta is about 14.6 degrees. So what does that mean that our final answer is? Velocity vector has a magnitude of 23 meters per second at an angle, of 15 degrees. Now, why did I round so much? Well, it has to do with the information in the original problem. You see, in the original problem, we only knew the velocity to the nearest whole meter per second in both cases. And we are, after all, adding. We're adding vectors, but we are adding. And we only knew the angles to the nearest degree. And so that's how we'll keep it for our final answer here as well. And that's it. That's how you use the component method to add two or more vectors. Any questions? Oh, wait, I can't answer them. All right, you go ahead and practice this on your own. See you next time.